I think Chris is best. Okay, but ideally, we like a system to automatically construct this, right? This is what we get. Okay. And so, right, so what we found is, we've been working with the Berkeley modes, is that for protocols that use broadcast, when you get into high density, and if you're using CSMA, you get channel collapses. Obvious. Okay. And one of the reasons you don't see it so much in something like 802.11 is that if you're using unicast, it's easier to sort of limit the resources and use feedback in order to keep the channel from collapsing. Okay. So something in 802.11, like for example, we have RTS or CTS, right? That's actually a nice way to try to control the channel utilization. Okay. Where in broadcast, you're not getting the feedback from the receivers. So really the challenge that we're going to attack in this work is how to maximize the number of receivers of a broadcast packet. Okay, we want to do that in a distributed way. We don't want to add a lot of extra protocol overhead, okay, in terms of extra messages or exchanges or anything like that. Okay, and we want it to be fair in the sense that everybody has roughly the same number of receivers in a broadcast packet.
Somehow it seems as though what you're saying makes sense, right? Except that when you say, oh, unicast is better, it means you give up whatever it is you're doing in the broadcast.
Right.
But you don't replace one broadcast with 10 people with 10 unicasts.
Right, no, right. So unicast, right, if you're not doing the same thing, in general, it's easier to You don't replace it with 10 unicasts. Just doing unicasts. So, are there any questions on the goal here of this work? Okay. It's fairly straightforward, right? Although we'll see that as we move on to the talk, it's actually not that easy. Okay, so what we're assuming for these cloud networks is that they're really developed in ad hoc style. Okay, so you just throw nodes around. There's nobody telling each node when to go. There's no time division multiplexing. Every node just has to make decisions totally independently. Okay. The other assumption, which may not be true, depending on what you believe, is that there's few channels available. Okay. So in the Berkeley modes, we have one channel. In 802.11, for example, you have like 11 channels. Okay, so you don't have a lot of channels. There's other schemes where you may go to a different class of radio where you've got lots and lots of channels. Okay, so if you've got lots and lots of channels, then there's other ways to alleviate this problem. But I'm not going to take that going to many channels approach. Okay, we're assuming that you use CSMA, and we're assuming in this work that, which also people may debate whether this assumption is true or not, is that there's really a predictable mapping between range and power. Okay, so what we're going to do in this work is we're going to do everything in terms of range because all of our analysis is done using geometry, right? So when computer science is done, nice discrete geometrical approaches. Okay, and then we're going to assume that somehow in the layer you can translate this number you get out for the range you want to set into the power circuit. Okay, we're not going to deal with that with translations. Also, other people do that. Okay. Right, so I just outlined the other strategies you could use to solve this problem. You could use rate control, channel control, or range. And the approach that we want to use is ideally, because we have this distributed ad hoc system where we don't want any central control of anything, and we don't want to send extra protocol messages, is that a node should just sit there somehow passively observing, okay, its local density, okay, and the local sending rate, okay, and then try to perform this range control in order to get this maximum broadcast coverage. And then once it figures out the range, then it goes back and sets the power, okay, to conform to the range setting. Okay, so where would you kind of put this in a real system? Well, I would imagine that you would put it somewhere in layer 2, okay, classic, OSI kind of layering scheme, somewhere sort of between the logical link control and the math layer itself. Okay. So you got messages coming down. This is kind of what deals with the formatting of like the frame, putting the checksums and all that stuff. Okay, you would stick it in here at this level, okay, and then this was the thing that actually tries to access the channel. Okay. So the math layer, listen, make sure nobody else is sending it. So hopefully I gave you enough motivation. Okay, so now the rest of the talk, what I'm going to go over is the way we approach this problem is we try to derive an analytic model, okay, using a lot of simplifying assumptions, okay, to derive an optimal setting for a given situation. So given a bunch of local observations about density and sending rate, so we derive an analytic model that gives us the optimal R set. And then we're going to try to take this model, okay, and apply it to a real algorithm. Okay, and we'll see that when we apply it to a real algorithm, when we ran it even just in simulation, okay, a lot of the assumptions about this don't hold, and so there's a bunch of, I don't know what I call them tricks, but there's a bunch of other compensating things you have to do in order to get it to work. And then I'm going to show the simulation results that show that a bunch of compensations plus the analytic model actually work, and I'll wrap up with some future working. Okay, so how would you try to find optimal coverage? Well, analytically, okay, I guess you can't see these. There's two curves. One is, okay, so there's two sort of opposing forces going on. If we want to maximize this idea of a broadcast coverage, okay, we can just set our range to be as far as we can go. Now that works if you're the only node out there actually sending it. Okay, but if everybody does that, then it doesn't work anymore. So what does that look like mathematically? Well, as I increase my R, right, the number of nodes in the range goes up. But the number of nodes which experience interference from neighbors that I'm trying to send to also increases, right? And so at some point, this curve here, this interference curve, right, the rate of that thing goes faster than the rate of the curve of nodes I'm adding by increasing my range. They eventually they get channel collapse and then nobody gets any messages. Okay. So if we plot the distance between those two curves, right, we should get a curve like this with some max. So one curve is if I expand the range, I can reach more people. The other curve is as everyone expands their range, the number of nodes that experience interference. Okay. And so we want to set this value we're calling R0 is the range that gives us the highest expected coverage. So expected coverage is just when I send a packet, right, how many people, what's the expected value of the number of receivers that receive the packet correctly?
So the first curve, right, is just kind of an R square, right? Some density.
Yeah, it's based on some density, you get some curve.
Based on, but what's the second curve?
So the second curve is really, if I send a packet, how many nodes do not receive the packet because they got interfered with by some other transmission?
So it seems like there's some MAC protocol that is sort of limiting these other transmissions, or
no,
or that there's some spatial density of other transmissions out there somewhere, or maybe that's what you're gonna go through.
Well, right. This is just conceptually. So conceptually, there does exist some curve. Okay, we don't actually compute this really.
Yeah.
I'm just trying to get at right that there is some curve. Right? You can, I mean, if you have a simulator, for example, you could go plot each point of this curve. But we're not going to derive this curve analytically, but there does exist some curve like that.
But it's not the number of nodes. Like you could, for when you first drew it, I thought you were saying, oh, it's the number of nodes that this transmission interferes with.
No. It's the number of nodes that you're trying to reach, that you could potentially reach, but have failed to reach because they experienced some interference from some other node.
Okay.
Right?
Yeah.
So is your interference model that if you receive two different transmissions from two transmitters, then start?
Yeah. So it's a very simple model. You're in the range of any node and stuff. So, okay. Right. So we're going to derive this general formula for coverage versus the environment at some radius. Okay. And then we just, if we take the derivative of that, I think we can find the maximum. Okay. And so here's our analytic model. It's very simple. We just assume that nodes are distributed evenly in space. Nodes send packets with on arrival rate. That packets have a constant size. They're using CSMA. That all nodes use the same transmission radius R. Okay, so if we're given R, right, we want to compute the expected coverage, we assume all the nodes using the same R in order to make the analysis happen. Okay, and the wireless model is very simple. Okay, so everyone within R can potentially receive the packet, and if more than one transmitter is within distance R to the receiver at the same time, then the whole thing is correct. Okay. And then so really the parameters we're looking at are what we call lambda S, which is the spatial density, lambda P, which is the arriving rate, and this transmission time. Although we're not going to vary transmission time in this work. No. Why do you need a solid arrival rate?
No, not the.
This isn't node arrival rate, this is,
For the node distribution.
oh, spatial distribution. So we're using geometric scheme, so you'll see. Okay, so I'm not going to get into this build too much. This is what people in this building do more than what we do, which is try to come up with a practical model mapping between the power and the range. Okay, so this is just showing that the actual. This is a more realistic formula. This is the one we use, which just says that the power of the receiver node has to exceed some threshold in order to receive the packet correctly. And this is the power between the sender and the receiver, and it's going to be a function of the actual power between the sender and receiver, the distance, and all the sum of all the other powers of the other nodes, and then some noise function. Okay, so we're going to abstract that away. Not worry about that. Okay. This is just labeling all the things, the inaccuracies that we have involved here. That's one inaccuracy. Another inaccuracy is that we don't account for any unicast traffic when we derive this coverage. Right, assuming all the nodes have the same range. We assume all the transmission times also arrive at some process, although if you use CSMA, that's not really true, right? It becomes correlated. And you'll see our geometric approximation coming up in a couple slides. Okay. And so these are just, this is one simplification we did in order to make this problem of CSMA making the transitions dependent go away. We just assume that all the arrivals are actually independent. Okay? But the important thing about making this simplification is that it's conservative to R0. So what do we mean when we say it's conservative to R0? It overestimates the interference from neighbors. Okay? This is actually this simplification is actually important because in all of our simplifications we're going to make, we're always going to err on the side of being conservative to R0, so making R0 too small. Okay? So if all our simplifications make R0 too small, at the end we'll get some R0 that's too small, okay, and we can reapply some fudge factor. Or we can just leave it as being too small because, you know, maybe we want to err on the side of not reaching as many neighbors, but then we don't have to worry about the channel collapsing. Okay? So that was a nice property of our simplification. So we're always making R too small, okay? Because we're interfering. CSMA is going to slow down the transmission in some sense over overestimating. Okay. All right, so here's the geometric approach, which is the expected coverage of a packet is really the number of nodes in range, okay, that you could potentially reach, right, minus the losses from nodes that are in terminals to you. So those are nodes that can't detect your transmission, you transmit anyway, and then a third node that you could have reached gets the packet clobbered. And so the random variable we're going to use is the distance of the closest interfering node. Okay. And so what we did was we derived the CDF of this function, okay, which is this probability of an interfering node being, you know, x units away. Yeah.
Back to the collapsing. I mean, suppose you go beyond the 2R0 just a little bit.
Okay.
Does the channel just simply collapse, or does it deteriorate very slowly as a function?
I don't understand your question. If you go beyond 2R?
No, if you go beyond the real R0, not the approximate.
Oh, no, the model will show that it collapses slowly. Yeah, so what the model will say is that coverage will start going down, but it goes down as a continuous function. It doesn't go to 0.
Well, I guess I'm getting at is it very important to err on the side of underestimating R0 and overestimating? I mean, if it collapses very fast, then...
Oh, so right, I guess, right. So the question is, you know, if that curve is very steep, then you would want to err probably on the side of less coverage and not having channel collapse. If that curve is like very drawn out, it's not so much of a problem. Yeah, I would agree with you, but we haven't looked at the shape of that curve. We could with our...
Well, in fact, the shape of the curve, as you'll see with the mapping later, depends in some sense on random S and random P, right? Sometimes it's fat and sometimes it's skinny. So when you'll see our mapping, you'll see that this coverage curve sort of shrink and
No, but we don't have the we don't have.
Right. Well, my only point is that there's no single shape. Right?
No, that's true.
Right.
That's true.
And so since it changes depending on the parameters of your system, you really want to err on the conservative side, just in case where the coverage is, the function is thin, you really don't want to fall over.
Right, in a very dense system, the curve will be a lot steeper than in a sparse system. So, but we don't, I mean, we haven't quantified what those shapes are. Yeah. Okay, so then we can find the expected number of failed nodes for each point in this PDF. And then what we do is we subtract that from the amount you could actually reach to get the expected number. So let me give a pictorial view of this, okay? So what we did was, the way we actually did it, and this is showing you this nice trick, which is to actually start from, so here's a node that's transmitting, okay? Here's its transmission range, okay, which is R, okay? Then sort of any node that sends a packet, okay, in this torus of 2R, okay, or in 3 dimensions would be a 3-dimensional torus, okay, could interfere with some nodes in this inner circle, okay? So that's what this red area is, okay? Okay, and the way we build these functions is, which shiny index is, you may want to start here and work out, but actually that way it's a lot of math that's really icky. It becomes a piecewise function at that point. So you want to actually start from here, okay, and work it. So this is like the probability that the node, the closest interfering node is within X distance to the outer edge of this torus, okay? Right? So this is the position of the interfering node, okay, times the number in the affected area. Okay, and that gives us the, right. Then we take that PDF, okay, and we multiply it by that number, okay, and we integrate over all possible values of X, which is just really the range, right, 0 to R, okay, and then we get this expected number of failed nodes. So that's the strategy, right? Okay, but we had to make some geometric simplifications, okay? So we spent, I don't know how long, at least a month, maybe more than a month, trying to figure out, okay, so if you had that function, then you could also try to say, well, you know, we've got, what's the probability of multiple nodes being here, and then you have to figure out all these overlapping areas, okay, and I got like really hairy areas with like at least a month on that, but, okay, so eventually we threw all that out, okay, we just said, okay, what's the probability of the closest affecting node, okay, forget all the other nodes that might transmit, all right, and then just approximate all this shaded region here with a torus that looks like this. 1R, just select this one. Okay, so what we did was we said, okay, in reality, what might happen is something like this. You have multiple nodes transmitting, okay, and their affecting areas overlap, okay, and they overlap each other, okay. And so computing the shape of this, computing the actual area, not the shape, but computing the area of this whole thing is pretty hairy.
Yeah.
Very difficult, right? Because you've got multiple intersecting circles and...
Yeah, we agree. So what's the blue?
So what the blue is if you just take all these multiple intersecting circles and say, which of these nodes is the closest to R, okay, and build a torus out of that area.
So you're upper bounding.
Yeah, it's an upper bound, right? So what this provides is a conservative estimate again, okay? Right? So we just said, okay, so what would have happened here is this node, let's say this node is the closest, right? We just said the affecting area is equal to a torus that would have been right, centered around that.
Ah, okay.
Okay?
Yeah.
Okay, so that's what the blue area is. So it's upper bounding this.
Right.
Okay, so that makes the analysis tractable. And actually, as you'll see later, so we verified this with simulation. It's not really that far off, actually. It's 20% error at most. So, but again, it's conserved to R0. So we know that using this analysis, using this simplification, okay, our analysis is going to make R again small. Okay, and so what we had to do then is go back and see by simulation how far we were off. Because we weren't sure this was going to work. So then if you could go grind through it, I have copies of the paper if people want it later. You end up with this set of equations. So the expected value is really the expected number of nodes in range. It's pretty straightforward to get. Okay, times the integral of this. This is the PDF, and this is the number of expected nodes of the failing rate. Okay. And then we got to this analysis and said, oh, it's not a closed form formula. So that was kind of bad. But given that this isn't a closed form formula, it's still computable. It's not a closed form formula. We can't solve for R0 directly. Okay, right? This is really just an integral from 0 to R. So what do we do now? We used an extrapolation technique in order to make this problem tractable, so we'd use in practice. Okay. So the idea with this extrapolation technique is we solve R0 for a specific set of values. Okay, so for a given density, okay, and a given arriving rate and a given t, okay, we can figure out what the optimal R what the optimal range is for that set. Okay. And you can just integrate that function numerically like you can figure that out. Okay? And then we assume T is stable, so we don't worry about that anymore. Right, and now what we do is we build a set of extrapolation techniques that let us go from, okay, any given density and rate, okay, to a new density and rate, okay, by using a set of extrapolation techniques. Okay, so what it says is, if I give you the optimal R0 for a given density and given rate, okay, and then you give me a new density and a new rate, okay, I have a set of equations that I can use to figure out the new optimal R0, okay, without computing in directions. But I need this initial point to do that. Okay, and so that makes it tractable to actually use this technique.
You actually have 3 independent variables. Like in the sense that somehow when you look at this optimization, you can't somehow reduce the number of parameters by, I don't know, the ratio of lambda s to lambda p, or
Well, you see,
the,
oh, you mean,
you know, the kind of,
you know, lambda
these
s.
kinds of problems, you often get situations where it turns out there's some
relationship, right? So
Yeah.
we use some relationships between lambda s and lambda p in these extrapolations. The problem is they're not really exact; they're an approximation. So you could have, when you did the analysis, said, well, we'll just assume they're exact as well, but
Yeah.
you didn't do that. So yeah, but yeah, no, you could try to relate rate and density into one variable. We didn't do that to at least build the initial
Or usually
point.
the lambda and the t are often, you know, in all these things where you're counting interference.
Keep the length of the time of the packet.
Yeah, but somehow it should, like, you should be able to normalize everything by unit
Yeah.
one and change the arrival rate. Sort of have the same problem.
Oh, yeah, I see. You could try to, yeah, we didn't do that. Actually, you could try to unify the arriving rate of time as well.
Yeah.
No, we don't do that.
It should be per capital T. The rate should be measured in
Per capital T, yeah, and then you can try to unify it. And that's a good feedback, actually. Okay, so what is this, visually, what is this extrapolation technique does? Well, if there's some surface here, this is optimal range for a bunch of density and rate, then we compute a single value here, and then we can get to any other value on that surface. So what's the first extrapolation technique is sort of assuming that the systems have what I call constant shape. Okay, so what that means is that, let's say we had two systems, okay, and they have the same arriving rate but different densities, okay, and we know the optimal range for one of the systems, okay. What I can do then is I can alter the R, the range, okay, to obtain the same number of expected nodes, okay, both in the circle and in the torus. Okay. And then I know that the expected coverage of system 1 is equal to the expected coverage of system 2, okay, just based on geometrical reasoning. Okay. So if I knew the expected coverage here, let's say it was 5, okay, and I have the same arriving rate between this system and that system, okay, then just expand the range here until I get the same number of expected nodes in here and here, and then know the expected coverages.
Yeah.
So this is basically the spatial rate is per house square. Just like
The time rate is per unit T,
Yeah.
visits per unit A, or
But,
per
right, but
unit B.
this mapping is exact. We'll see later that
Yeah.
another mapping is exact. So the next thing about this mapping is exact. Okay. So the next one, the next extrapolation is what we call constant packet volume. Okay. So the idea is that if you have two systems, okay, one system is more dense than this system, okay. But if the rates are, you could imagine that the coverage should be the same if the total number of packets you expect coming out of here, okay, is the same as coming out of here. So, so it really says the ratios of the coverage equal the ratios of the parameters. Okay, well the problem is that's not exact because that's what I had. Right, so this extrapolation 2 is really approximate. Okay, so we have both. Because we have more nodes, there'll be more collisions. Okay. So it's not exact in that sense. Okay. But there's an opposing effect, which is because of the higher density, there can also be less collisions because of CS of A. Okay. So you've got these two opposing effects, but in the end, we didn't know which one of their. It's probably not exact. It's probably approximate, but it seems to work reasonably well. So those are two extrapolations. Okay, so if you go through the math and you combine the two extrapolations, you get R0 should equal the square root in 2 dimensions of some constant times this, like the spatial density times this function.
So is the non-exactness of that a function just of the fact that it's really CSMA? But if you said, no, our model is it's plus on arrival.
If the model is right, not CSMA at all, then it would be exact.
Then it is exact to that model. Yeah.
Right, so then you grind down, so then you're seeing a fairly simple equation. So, yeah, so this, solving something like this is probably tractable. Well, actually, even in a real system, you wouldn't even solve that, you would just use the extrapolations. Okay, so now what we wanted to do was verify the extrapolations, okay, and all our simplifying assumptions. Okay, so what we did was, we ran a ton of simulations over a wide variety of densities and waves, and compared the ranges that came out of the simulator, the optimal ranges that came out of the simulator to the optimal ranges predicted by the analytic model. Now, the way you do this quickly is you get the R0 from the analytic model, okay, and then you go back and you plot a bunch of points around that point and see if the optimal range in the simulation, how far off it is. So it's actually not that hard. It's not that computationally attractive.
So what does the simulation actually do?
It just lays out a bunch of nodes at random through space.
Yeah.
And then they just start sending packets randomly using CSMA.
Oh, they do CSMA
Yeah.
simulation.
Yeah. And then you see when you send and then you just, over a long enough interval, you compute the coverage, or, right.
So you run a simulation for different range.
For each range, right, you run a simulation for each range and then you're computing the coverage by just observing how many nodes actually receive the packet. And that gives you the coverage, and then you keep varying the range until you find where that coverage is maximum.
And then you do that for a bunch of snapshots somehow?
Yeah.
So you get.
Yeah, you just keep doing it over and over again.
But in the simulation, you actually use the model of the analysis for ranging.
Well, no, in the
or you use more.
No. In the simulation, so what I meant was the ranges you pick to actually try in the simulation are based on the analytic model, so you don't have to do a huge number of points. Okay, but in these simulations, you're not actually running the algorithm to pick R. You're just blindly picking R.
No. The range to power model.
Yeah. So there's first you convert range to power, right? But then, for instance, you could be simulating something where you really use this coverage model, like you hear somebody up to radius R, and if the other transmitters are more than radius R away, it's fine. Or you could use more of like your original SIR kind of Gupta Kumar NS2 kind of. You collect a lot of interference from the other transmissions and.
No, we didn't do that.
So your simulation uses the ranging model.
It just uses a very simple ranging model.
Okay.
But because this set of simulations was just trying to verify the assumptions of the model.
Yeah. Okay.
Right, and so what we found was that kind of at most it was 20% off, which was actually pretty encouraging, and some were less. Okay. So kind of if you add some fudge factor of maybe 5% or 10%, you can usually see. That was a nice result, actually. Okay. All right. So now we'd like to take this analytic model, okay, and actually use it to build a distributed algorithm. Okay. So what happens here is.
No, you're good. You started late.
So,
We started at quarter of.
All right. Okay, so we have this analytic model, right, that gives us range versus density and rate, okay, and packet size. And we have a way to extrapolate that to any point. We need to turn that into a real distributed algorithm, okay? And so this was not that straightforward, actually. There's a bunch of tricks we have to do. It's basically the bunch of little fudge factors and tricks we have to do is because the model assumes you have perfect information and makes a bunch of simplifying assumptions. Okay? So if any more realistic network, you don't have perfect information, okay, and the simplifying assumptions don't hold. So most of this came out of not having perfect information. Okay? So the style of the algorithm is pretty straightforward. You wait, you don't adjust the range except over an adjustment interval. Okay, so you wait a certain number of broadcasts, okay, until and make these observations. Okay, and at the end of this interval, then you reset your range. Okay, that's the style. And so during an adjustment interval, you're trying to build a neighbor list. Okay, and neighbors expire if they're not refreshed for 5 intervals, Okay, and currently our interval is 20 broadcasts. Okay, this could be some tunable parameter. We're going to use 20 so we work pretty well. Okay, the other thing to collect is the average send rate of the interval. Okay, so you get those two pieces of information. Okay. At the end of the interval, you compute the density. Okay, and using fairly simple models, you just basically collect the range to each neighbor and then use a simple kind of spherical model to compute the density. Okay. Then you set the range and use that range for next one. Okay. So that's the style of the algorithm, but it never really works that easily. Okay. So we had to do basically 4 things in order to get it to work in practice beyond that very simple approach that I mentioned. Okay. The first thing is, when you first start the algorithm, you need this like warm-up period. Okay. So you don't want to just like take the first interval and then set your range and then you're off, you're done. Okay. You need to actually adjust your range in this special warm-up period at first, okay, in order to try to get a reasonably accurate density estimate. Okay, so this special warm-up period. Okay. Another thing you have to do is you have to differentiate between when you're overloaded and underloaded. So if the channel gets overloaded, then you obviously want to cut your range back pretty quickly, okay, in order to get an accurate density estimate. And if you're underloaded, you want to expand it. Okay, so you have to during this warm-up period, you have to disambiguate those two things. Okay, and then outlier consideration. Okay, so even if you distribute nodes randomly, okay, sometimes like one node will be really far away. Okay, or maybe a few nodes are really close. Okay, so somehow you want to throw away outliers without throwing away too much information. Okay, so we have to deal with outliers. Okay, and then in order to get more accurate density estimates, especially in non-uniform networks, okay, we had to use these extra longer range push and what we're calling push and pull messages. Okay. I'll get into what these are later, but the idea is that occasionally you'll send a message with this extended range, okay, and the idea is to give to give your neighbors like a better overall picture of what the system looks like. And but you don't want to do that too frequently because in some sense you're loading the channel more than necessary when you have longer range messages. Okay. So what does this initialization warm-up period look like? Well, you got to start with some R, so you have this initial guess. Okay. And then you wait at least one interval.
So an interval is like 20
broadcasts. You just sit there watching for every 20 broadcasts.
You just hear 20 different people, 20 different broadcast messages by some number of people. Not
Yeah.
20 of your own broadcasts.
No, it's actually 20 of your own broadcasts. It's 20 of your own broadcasts. It's 20 of your own broadcasts.
Okay. And each time you collect the number of neighbors,
Yeah.
and that's called an interval.
Yeah.
And then if you go 5 intervals and you haven't heard from somebody in any of them,
You throw that back.
you assume they're dead or missing.
Right. So in this warm-up period, right, you have to wait one interval to what you said. Okay. And then you're not going to adjust. You're not going to set your R according to this formula until you've seen sufficient neighbors. So we'll get into that. Then you have to disambiguate if the channel is overloaded over this interval. Okay.
So what does that mean? Like, so if you transmit with too small of a range, right, and no one hears you,
Yeah.
and then you get like very few replies,
Yeah.
and that can be confused with an overload situation.
Well, right. If the channel is too overloaded, you may be getting a lot of corrupted packets, and you may not just be getting them up later.
So at the layer of thinking about this,
Yeah.
the other possibility is people have ranges that are way too big, and
Everybody's range is way too big, and everything's getting corrupted.
and you're just not seeing any neighbors.
Yeah, because
How
everything's
do
getting
the
corrupted.
thing distinguish?
We just did a really simple thing, which was initially we just said if you didn't get any neighbors in the interval, then the channel's overloaded.
Then the channel's what?
Overloaded.
Well, what happens if you didn't?
That's not in the channel, but it didn't get any packet.
Right. Yeah, you're not hearing any neighbors.
But it says, channel.
Yeah, you sent the channel, but you're not getting any packets.
But how can you tell that isn't that, oh, it turns out you used the power 1,000 times too small, and you never reached anybody?
Well, no, because
And that's your question again.
It can be energy, but just not getting anything that is correct.
no. So I think you're going to. If my power is too small, nobody's going to hear me, but I might hear someone else. The protocol has no feedback. It's just, doesn't has no feedback, but there's no direct feedback that way. It's not like when I send a broadcast, in this level of the protocol, I'm going to get responses necessarily. I'm relying on higher levels to be responsive, but I'm not making them easy to respond to.
So that's just only what you could.
Yeah, you can think of them as sort of at this level. Yeah. Right, so the way we detect overload was very simple. Just if you didn't get any neighbors in your home, was overloaded. You can do something more sophisticated. You could like reach down and more layers. And so
Okay,
every
but
packet that
it's
was
nicer
corrupted.
not to. So-
Yeah, it's nicer not to. So.
But how do you avoid like just driving your range right to, you know, epsilon 0, boom, like if you follow this, right, suppose you get to 0 range, you turn your transmitter off.
Yeah.
Because you keep saying, oh, I don't hear anybody, I'm in overload. Like how do you avoid?
Well, that's what the full message.
Well, you'll see later there's these extra long range messages, and if you're not hearing enough people, if you're not in overload, but you still haven't heard sufficient neighbors, you can expand your range. So that there is an expansion there.
And sometimes we just arbitrarily expand anyway, right, just in case we get
Yeah.
wrong about shrinking, right, and then when you expand.
Well, right, there's these extra long range messages to force expansions. Right. Okay, so you're going to loop around until you get enough neighbors. That's the second thing. Okay. And so if there's not enough neighbors based on the density that you get from the first interval, okay, then you say you're underload, and then you're going to expand the range to cover twice the volume. And the way you can get this expected N is you can work backwards from the density estimate that you have to get this expected N. So that's the equation. Okay. And so if your neighbor list gets big enough, okay, then based on the formula you can, and the analytic model, so right there.
No. So the assumption, I'm just trying to understand this. Is that if point signal energy, that will eventually result, and power, that will eventually result in communicating other guys as well. In other words, they will follow. So that's the only explanation why how my power is going to result in communicating.
Yeah. Right. I guess the only at this layer we do have these special long range messages.
No, that's okay. But I was saying the
Yeah.
assumption is that I'll get that way. I get feedback.
Yeah.
So the assumption is that everybody's sort of running the same protocol,
Yeah.
and there's no feedback, right? So if I'm expanding, likely other people are expanding.
Right. So if nobody's sharing anybody, then everybody expands.
Yes, okay. That's what I'm
Okay. Okay. So that would keep everyone from shrinking.
So wasn't there some desirable value of expected N? Was that somehow an outcome of the analysis? Like that the number of people you would have liked to have in range on an expected
Right,
value
so-
basis is some
Right. So
number?
the coverage is sort of this expected, right?
Yeah.
Say for a given density, I should cover this many nodes, I should see.
Yeah, but you could use it at the optimal R0, like, as part of, here's one of those questions about how the scaling works with is it always that what you're really doing is that you want to reach approximately
600.
6 to 8 or 600 to 800? You know, there are all those little packet radio papers where they always want it to be sort of in contact with 6 to 8 neighbors. I mean, I know your model's different, but maybe you have some other number which is really. But
We have a static N, while ours is different. So we have this N just because we don't want to make inappropriate estimation before we get enough information. While others is in the 6 stages of that.
yeah, but I guess the question is there really some best number that you would have for some that?
And not the best, but from the modular thing, when you arrive at that R0, at least you should reach this many nodes. And you assume when you reach, when
So,
you
okay, so let's put it this way, like, the best R0 times lambda S, or the volume of that R0 has times lambda S, is that a constant?
No, it's not.
Okay.
But yeah.
So that N is from the previous model that you showed,
Yeah.
expected N.
Well, right. So coverage is expected N.
Yeah.
This is just, as Cheyenne said, this is really, you want to make sure you have an inaccurate density estimate, because that throws everything off. So you need to make sure you have collected enough neighbors that you're getting some reasonable estimate density. Okay.
At the level that we're working with, there's no obvious best end, right? If for example, you're routing, the best end might be just one. Right? If you're doing some other things, the best end might be really big, depending on whether you just want connectivity or you want like to reach as many people. So since we're working at much below the application level, right, there's no knowledge of what the best end is. So it's
I'm just
not
trying to maximize that. Okay. So how do we deal with outliers? Well, we use, when we compute the density, we use the median density computation. So what does that mean? It means that you can think of sorting the neighbors based on distance, and then as you move out from neighbors that are farther away from you, okay, you compute the density using that subset of neighbors. Okay, so you take the closest neighbor, second closest neighbor, third closest neighbor. Okay, and then for each of those, for the first neighbor, you compute the density. For the second neighbor, you compute the density using the first two neighbors. And for the third neighbor, you compute the density using the first two neighbors. And then you can get this list of all these densities you computed. Okay, and we take that list and we sort it, and we use the median of all the densities that we compute. Okay, and that actually was very good at controlling this outlier problem, okay, by using the median density. Because one node that's far away could like go the average.
But you eventually want everyone to use the same R0. Yeah?
In the
Yeah,
uniform
maybe
network,
now it's
in the uniform network, yes. And you'll see that later. In uniform network, yes. In non-uniform network, no. You hope that they just use R0 like in the local density. Right. Okay, so then the last thing that we did was what we call push and pull messages. And these were, as I said before, just you extend the range of a normal broadcast beyond the R0 setting. Okay. And so pulls are really used so that your density estimate includes any hidden terminals that may be in your range. Okay. So what you do is for this pull, when it's time to send the pull message, okay, you increase the range to such that you double the volume. Okay. So you could say, well, hidden terminals really double the range. But we found actually that doubling the volume was a good compromise between sort of overloading the channel with this extra range and getting a reasonable density estimate. Okay. So, right, so when you send a pull message, you send it through 2/3 of R. Okay. And then pushes are used to account for the problem that, especially in asymmetric networks, or not in non-uniform networks, you have asymmetric range settings. Okay. So in your density estimate, you should really account for all the nodes that you're impacting by sending your message. Okay. And so the idea here is that you set your range for a push message to the range of the node that you've heard from that's furthest away. And I didn't include the picture here, but the idea is this is a whiteboard.
Yep.
Okay. Right. The idea here is that let's say we had some cluster of nodes here that have a short range. Right? Okay. Let's say we have like one guy way up here. Okay. So this guy sort of, there's nobody around him, so he has a really long range, right? Okay, so this guy's messages are going to impact these guys, okay? And this outer range node should know that its messages are impacting these nodes over here, okay? So these nodes, right, when they go to send a push message, since they can hear from this node, and this is the longest range node they can hear from, right, they'll set their R such that this node knows about them. Okay. And that's what pushes are for. To make sure that these nodes that are far away that are impacting a lot of nodes in a cluster actually know that this cluster's here. So that's the idea for push messages. Okay. And we found that we can get our algorithm to work by only having 2% of these messages, both 1% pulls and 1% pushes was sufficient for everyone to get a good density estimate.
Because that has something to do with having one or two of them in every 5 intervals. Like 5 intervals is about 100 broadcast messages, and you want to make sure you do 1 or 2.
Yeah, we did basically 1 every 5 intervals.
Yeah.
But I mean, analytically, I don't know how many would be required. Just try that. It seemed like a reasonable small overhead to get the density estimates to work. Without it doesn't work. The problem without those messages, right? You get effects where, like, this guy will dominate the set. You never get any feedback.
I have a question regarding pull messages.
Yeah.
So basically, you find some optimal range, some density, some optimal range, and then you double that range to check out whether there is somebody who's potentially the hidden terminal for you and who's gonna deteriorate your process. I just
Right.
didn't,
Yeah. So if there's hidden terminals that you're not accounting
just
for.
to then catch
Yeah.
those potential interference.
Yeah. So they know, so that they know you.
So if you have a geometry like this,
Yeah.
right? Like, the ultimate goal for your system, like, what do the R0s look like? Do those little guys there in the circle have little tiny R0s?
Yeah, so these guys have shorter R0s than this one.
And that guy would have some really big R0s.
They have a bigger R0, but it shouldn't have it too big, such that these guys will get screwed.
But
Right?
is it big enough?
There are a bunch of these guys out here, right?
How about suppose, like, he's really like this way out there all by himself?
Yeah.
Like, what's the goal of this? Is it then, like, he's gotta make sure to use an R0 big enough to talk to somebody there?
Well, yeah, he's got to use it. I mean, the goal is for him to maximize his coverage, so he's going to set his R0 as far out as he can to reach, as many nodes as he can with the forecast.
I think the really harder question in that scenario is should one of the guys in that cluster set his R big enough to reach the guy outside?
Right.
Right, the guy outside will set his R
Yeah.
really big so that it but not interfere with too many guys, right? But if you want
Right.
connectivity, how do you get one of the guys in the
Well, so I
cluster?
think that's the question, is it really to make sure that the network is connectivity? Like, is that a sort of a fundamentally like the basic constraint?
In this work, right, we're just trying to optimize broadcast.
No, I know, but you really talk about this network and you're talking about this, then you're really talking about some goal that sort of, that's beyond just what you're formulating.
Right, I guess
optimization.
there's been a lot of people that looked at connectivity, and they're just
Right.
trying to make sure that you're connected to at least one other node.
Right.
Yeah, the difference is the basic process. Therefore, you want your process message to reach that and whatever appropriate then number is.
Yeah, usually connectivity is more for some kind, like in a routing protocol where exchanging messages, it's more unicast, right? So.
The thing for us here is that we can't guarantee that there's connectivity, right?
No, there's
The
no
guy in the
guarantee.
cluster may not reach that guy out there.
Right. There's no guarantee of connectivity. What we found though is that in practice, at least for even the non-uniform network we've had, it's pretty good connected. But yeah, there's no algorithmic guarantee of connectivity. There's a lot of other work on that.
Yeah, sure.
Okay, so now I'm just going to try to, in the next 5-10 minutes, just give you some confidence that this algorithm actually works. Okay. So we simulated in the 3D environment. We simulated about 5,000 nodes in a volume of about 100 cubic meters. And the things we wanted to test were robustness to initial conditions. Okay. So if everybody sets their ranges starting off too high, too low, or sort of at random, does the algorithm converge? Okay. So that's what we wanted to test. We wanted to see the convergence speed, and then we wanted to make sure that the final ranges and coverage we get out are reasonable. Okay. And also that it's fair, right? So that everyone has roughly the same coverage, right? We also tested robustness to non-uniform densities, right? And we used the topology from the lab inventory. And then we wanted to see the effect on the higher level protocol, which we actually called the higher level. So we did a hop by hop localization protocol with range control and then without range control with a certain impact. All right, so here's just simulation results on convergence speed. Okay, these are adjustment intervals, so each of these are 20 broadcasts. Okay, and we see that for a variety of rates, each of these lines is a different rate. Okay, this is time. So this is the rate of sending a packet every 0.8 of a second, each node is doing that with 8. And then this is the average range that comes out. We see that we converge in roughly between 10 and 15 intervals. Okay, so you're looking at 100 to 200 broadcasts in order for the entire system to converge. And then this was setting your initial range to 3 and setting your initial range to 20. So just showing that it converges under different conditions. And then robustness, again, to initial range settings. This is the same experiment, but looking at the final ranges that come out. Okay, looking at histograms of those final ranges. Okay, so if everyone sets their initial R to 3, okay, for these different packet rates here, each of these histograms is a different packet rate. What's the final histogram that comes out in terms of, this many nodes had a range of 5, or this percentage of nodes had a range of 5, this percentage of nodes had a range of 8. Okay, so the interesting things of this graph are, first of all, that we're getting pretty nice bells, okay, which means that the algorithm is in some sense, at least statistically fair. Okay, the other thing to note is that for the higher rates, okay, remember that our simplifying assumptions about CSMA really apply to kind of sending rate, right? So we see the bell, the deviation is a lot tighter here, right, than it is over here, which is just what we expected. So that was nice confirmation of, our assumptions actually behave like we expected. The other thing to note was that both with the initial R's, one set too large and one set too small, okay, that the algorithm converges sort of the same bell for each one. It's just saying that. Even if you set your R very large initially or set it too small initially, you come to the same solution. Okay. And this is just showing the final coverage for different packet rates. Okay. So this was sending a packet every, on average, the rate was right 1/5 of a second. Okay. And you see the coverage, again, it's not quite as tight as the range bell, but it's still pretty reasonable. So it's centered here around 9. Right? And that's both starting with a long range and a short range. So those are the two curves. So, right? Start with 3 meters, start with 4 meters. Yeah, so hopefully that gives confidence support. Okay. Again, we did this similar kind of experiment. This is setting just the ranges totally at random. Okay. And then seeing if it converges. So this bottom line, I don't know if you can see it, is the initial ranges. Okay, it's all random, uniformly distributed. The end of the algorithm, okay, is that bell. Okay. Okay, and so we also ran this for non-uniform networks. Okay, so what we did was we took our lab inventory. Okay, we just made all the objects into points. Okay, so just the mean of the bounding box of the object. Okay. And then we ran the algorithm. This is the initial coverage. Okay, and we see here that the initial coverage is pretty bad, right? So if you didn't do anything, I'd say this is not really a bell curve at all. It's some kind of color curve.
What do you mean by
But it's,
so you make the objects into points and
well, so an object, like let's say I wanted to put a tag on an object like my laptop.
Right.
Okay, my laptop actually is better described by some bounding box than a single point.
yeah.
Okay, but so you have to sort of, in order to get the simulator to work, you have to reduce that to some point.
So we assume the tag is at the center of the object?
Yeah. So you just assume the tag.
I sort of assumed you're doing that all the whole time. So you're doing something different earlier?
Well, earlier it was random networks, right? So it didn't matter. There was no notion of object or anything. It's just
Well,
random.
like all like the previous simulation. So I guess I'm confused. Is this why it says non-uniform?
Yeah.
Right.
So I'm saying, how do we build a non-uniform network? That's
So what does
realistic.
non-uniform mean? I thought it meant that, like over space, you don't have some quantum distribution.
Right.
This is measurements for our lab. Remember that?
That's right. Your intuition's right. Over space, it's not uniform density.
Yeah.
It's non-uniform. So how do you get a non-uniform density? Well, we just took our lab measurements and used that as the non-uniform.
Oh, so the other ones were not the snapshot of the lab. They were
These
just like
were all just randomly generated,
space.
uniform. Yeah, you just pick random X, random Y, random Z.
All right.
So right. I don't know if that was good for. And these were for the actual lab measurements. What I was getting is how do you reduce each object until you describe the bounding box of
Yeah.
And what you see here is that if you don't do anything, okay, the initial coverage is pretty horrible. Okay. It's probably, the mean is probably under 1. So that says when I go to send the broadcast, okay, on average, right, less than 1 node actually receives it. So, and then over here, after you run the algorithm, you get a coverage of about 12, which is much better.
So in the lab, it replicated 6x.
Yeah.
You made 6 boxes.
You took the lab and you made 6 copies of it. You made.
Does it matter if you
Did you make the
lay
lab
it
taller?
online or 3x2 grid or?
I think you did 3 by 2.
Yeah.
When you
Like when you
replicate,
make 6 boxes in the lab, how you build, how you play with the boxes doesn't matter.
Oh, here, because the height is too small, it replicates around the Z axis.
You just stacked it up 6 tall.
I thought you didn't make a 3 by 2 thing. You stacked them all vertically.
Of the height and the.
You did some width too, right?
Yeah, height is relegated to 3 times.
Okay,
and
and width is
width
2.
2 times.
Oh, okay, that's like a 3 by 2.
Right, but 3 high and 2 wide.
When you say you don't do anything, you mean they just randomly choose some
Yeah.
One meter.
Oh, no, they all pick 1 meter. So they all pick 1 meter, which you would think is reasonable, but even then, yeah.
What is coverage?
Huh? Coverage is when you go to send a broadcast, on average, how many people receive that broadcast? So, right, so here coverage under 1 means you're doing a lot of broadcasts and not very many people are getting it. Okay. And then, so here's the impact on the localization protocol. This was a simplification of APS, which is Dragos' protocol. And so what this is showing is over time, okay, this is sort of like a stack graph. What's your localization error? So how close is your computed position to your actual position? Okay. And you can see here that, so this is your positions within 0.2 meters, 0.5 meters, 0.1 meter. Okay. This would be at 0.1, 0.2, 0.5. Okay. So if you use range control, okay, not only your position is more accurate and it converges faster than, not that much faster, but your positions become much more accurate than if you don't use range control. And it's just, you know, if you look at this, it's not hard to see a lot because you're not getting enough information in the broadcast.
Can we see artifact of stacking things are complicated because typically things tend to be flown around that.
No, I don't think it's in the stacking as much as if we go to the actual, see what happens is, I should have had a picture there. Okay, so what happens is that some areas like along here, these are the desks, they're so dense that when you set even your range to 1 meter, you cover like 50 to 60 minutes, like that order of magnitude. Okay? And so the channel just like collapses in here, doesn't work anymore.
So they end up using very low power, so they only talk to the
Yeah,
speed,
only talk to like in the simulator, right? These guys are going to be talking just within here.
So what's your range of power control? You're assuming floating point.
We're assuming floating point, just yeah. Which isn't well, yeah. I would argue that
that's time. Power.
It's not that unrealistic. What's more unrealistic is that you have an exact mapping between range and power. That's in, so we see with the modes is that that's really hard to actually get in a really nice mapping. You can get a mapping, but it's never that exact.
And then we use the floating point for $10.
But even still, right? He's right.
Yes, you're right. It's much more realistic than assuming.
Yeah. Whoops.
So someone here is an expert on this APS localization protocol.
Dragos is bad.
So like somehow, maybe you want to come and talk about it one of these days here. Yes.
Oh, you have a nice talk actually.
Because
yeah. So let me just wrap up with some future work and stuff. So this seems like promising. So we really need to do more forward building-wide simulations. I think our results are going to qualitative machines. We'd like to see what happens when you join and leave. I think this is more interesting. So how robust is this to, those going away and those coming back, stuff like that. Let's say one node comes in with like a really huge range. Okay, so somebody comes in with their power like all maxed out. That's everything. Okay. We'd like to maybe get some more realistic implementations playing off most here tonight. And what we really need though is this is the whole problem with the sensor network and ad hoc network community is that we need realistic high-level protocols. Okay, right now all the protocols we run are Chinese toy protocols people propose or something. It's not driven by more by realistic traffic patterns and realistic protocols yet. So this is sort of a chicken and egg problem, which is in order to get the system to work, we need protocols that work. In order to get protocols that work, we need realistic data. Right?
you need a really good application, right?
Yeah.
Like one that people actually care about.
Yeah. So I don't know how to resolve this. Just
Hey, we're in your boats too.
Yeah.
We're all
okay. Any questions on?
When you chose your initial range to be 1 meter, did you look at, if you have however many objects in a certain volume of space, did you check to see that 1 meter was reasonable in terms of what the average distance?
Right, so you're saying, would an administrator, is it realistic to choose this 1 meter thing? I think the answer is sort of yes, because if you go and deploy stuff, You don't want to have to reason about, well, you know, this is on my desk. I mean, you could argue people might think that way. Well, this is on my desk or something, so I'm going to set this knob lower, and this is, you know, in the bookshelf, so I'm going to set it higher, you know. Most people just want to pick one number or something, and that's it. Or
You
not
want
even
to
any number.
to figure out the number.
Yeah.
You don't want to diddle any, especially not 500 in your office.
I guess what I'm saying is that realistic, you know, if you're looking at a type of environment, like an office.
I think in an office environment, somebody setting it to 1 meter is fairly realistic, right? 1 meter is, you know, gives you a radius of about 6 feet, which is that size.
That's like, how many objects?
Although I think the argument for that, I don't think our argument was so much, look how much butter we got, right? I think it could have been half a meter, it could have been 1 foot, whatever you want. I think the point was whatever you set it, okay, we could get it, or it would work to get to sort of the right range.
And, well, the other converse argument is there's no single range in that environment that works for everything. So in the desk environment, you maybe want something like 1 foot, and if you're, you know, up in a bookshelf near the top of the bookshelf, maybe you want, you know, a meter or 2 meters. Right? So,
Well, bookshelf you want it small, right, because you're right next to another book.
yeah, that's what you
Yeah,
said.
here's the thing, if you're a book, right, you've got this little sensor embedded in you. Sometimes you're lost because you're in the bookshelf and they can't find you, right? And sometimes you're lost because you're not in the bookshelf and you're like, you know, under the sofa cushion across the room, right? And presumably a really good book with a nice algorithm will do some nice adaptive
Some adaptive
things,
things,
right?
yeah.
To help, you know, find itself. But it'll figure out, oh, I'm in the bookcase and use a very small one, or I'm all alone under the sofa cushion and
Yeah, I
it's
can't
really
really
good sound
yeah.
because I'm lost.
I guess it's sort of what I was saying, is that if you have a dense environment, you would want to set the range lower.
I think their point though is like, like, nobody gives cares what the initial range is. The point is, like, to start with anything, they want to make sure they get to the right range for the environment, right? Yeah.
Yeah, and whatever value you pick, I like your example of the book being lost. Whatever initial value you pick, you know, may not be true in the future. That's the right value.
So with the real implementation, you want to prove that this really works in a kind of an agnostic way to what is the wireless PHY technology.
Yeah. So even if we just did like 802.11 in mode, because they have much different PHY